Good evening, everyone. Watching the car chase on the news. So I'm a car chase junkie. All right, so some of you emailed me saying, look at my problems again, and I was in the middle of doing that earlier, and then Canvas locked up on me for some reason or another. So but I will be, getting to that. No real news to share from the campus, another positive test, but they always seem to report that stuff. Okay, so let's share the screen here. And we were talking about hyperbolas and parabolas today, and ellipses, all those conic sections. So a new page for today. Get text mode. 185. All right. Let me get this. All right, so let's do a kind of a recap here of what we got going on. Okay, so we have a sequence AN, and we're going to be assuming that the ANs are positive for right now. Okay, and what we discovered was that if AN is given by this function, then the limit as x tends to infinity of f of x is the same as the limit as n tends to infinity of a sub n. And because of this, we can use all of our limit laws. Use all of the limit laws. Hold on one second. I gotta check something. No. Okay. So we can use all the limit laws, all right? And so we had some results about monotone bounded sequence must have a limit, okay? So then we start talking about the series, which is adding them all up. K equaling, some starting point, A sub K. And what we found was this first result was that if this sum of the AK converges, then the limit as n tends to infinity of the things that we're adding up must go to 0. This is what we called the criterion for convergence, okay? So in order to have a chance to converge, the things that we're adding up are going to have to go to 0, okay? So we then started looking at some, specific results and stuff like that. And then yesterday we came across this idea of an integral test. So the way that the integral test worked was that if a sub n is equal to f of n, where f is continuous, at least on, 0 to infinity, or maybe starting at 1 and going to infinity, or for that matter, doesn't make any difference where you start. Go to infinity. That's supposed to be an n. Erase that. Okay. So if the f of x is positive and f of x is decreasing, and the limit as x tends to infinity of f of x is equal to 0, then the conclusion that we reached, the series the sum k equaling starting from somewhere and shooting off to infinity of ak, and the integral from, let's say, m to infinity of f of x dx both converge or both diverge, meaning they do the same thing. Okay. All right. And to kind of justify this, we looked at the harmonic series, k equaling 1 to infinity, 1 over k, which we know to diverge. We proved it by using D'Orsini's original argument. Okay. And this matched up with what this is. That's going to be the limit as t goes to infinity of the natural log of t. And the log is an increasing function. And so x is going to go to infinity. So they both are going to do the same thing. Okay. So I guess one way of thinking about why this is diverging is maybe these numbers, they're just not getting small enough. Okay. So what if we did something like this? K equaling 1 to infinity, 1 over 1,000 n. Now what we have is k equals 1. It's going to be 1 over 1,000 plus 1 over 2,000 plus. So one might think that, well, maybe this guy has a chance to converge because these numbers are a lot smaller than the other numbers. And there's a whole bunch of numbers in between 1 over 1,000 and 1 over 2,000 that we're not having to add up. Okay. But the integral test is going to show us that when I go 1 to infinity of 1 over 1,000 times x dx, I still get this same issue. Limit as t goes to infinity of the natural log of t, and it's still plus infinity. Okay. we developed something called the p-test, where we looked at the sum k equaling p to infinity. Now, I'm intentionally changing this letter. Okay. Oh, car turned around. Going the other way. By the way, you guys there? Somebody there?
I'm here.
I'm
Here.
Okay, cool. Got to do this periodically from time to time. All right. Man, I just love car chases. I wish they would have a follow-up show after the car chase, though.
Find out what happened in person.
Yeah. You guys all turn it on the news. You can watch it.
Is it local or?
Well, now they're in San Pedro. One time it was going on when my wife was at UCLA, and the car that they were chasing was her roommate Renee's car. It got stolen.
Oh.
They were watching it on TV in their apartment. Okay, so the p-test was, I had this series, and what we found was it's going to converge for p being strictly bigger than 1, and it's going to diverge for p less than 1. No more justification needed, okay? So for example, we can just say, if I start at 10 and go to infinity, 1 over the square root of n, that thing diverges because the p is a half. Old Leonard Euler figured out this one for us, 1 over n squared. And this thing converges, and I've even told you what it actually adds up to. Pi squared over 6. It's a kind of a strange result. Okay. So when we get to this place, and probably next week, maybe, we'll go through this argument. Okay. So the integral test is getting all this, done for us. All right. So one of the things that Euler kind of thought was that if a series is going to converge, like for example, his Basel problem, this is called the Basel problem. From Basel, what's it, Switzerland? Is that where Basel is? Switzerland?
I think so. I'm not sure though.
Yeah, well, that's where all the Bernoullis were held up, and because the Bernoullis were already there, there wasn't any room for Euler. But the Tsar of Russia was looking to modernize the country, and they made a great university in St. Petersburg and brought in Euler to head up the math and sciences stuff, and he stayed there pretty much the rest of his life. So if you look at a number line, like 1's a perfect square, 2, 3, 4 is a perfect square, but these things start to get stretched out, okay? And as you go down the number line, I actually did this for my son's, he had to do a fifth grade project. I think, no, it was a 6th grade project, something to do with math or science. And so I picked the, prime number theorem stuff, because I'm a nerd like that. And so I went into Ralph's and rolled out, I just own Ralph's at night. I just go in there and do whatever I want. So I went into the butcher and I rolled out a bunch of butcher paper that was really long, like maybe 20 feet long, a couple of them. And then I had a number line going 1 through 1,000. And then I had a number line going from 100,000 to 101,000. And I identified in these lists, like, okay, there's a perfect square, there's a perfect square. In here, maybe there was only 1. But what we were finding was that it seemed like you were kind of finding primes, no matter, you know, how big or how far out you look. So that the primes, this is what Euler reckoned. He said, so if the primes are going to be really abundant, then this sum of P being a prime of 1 over P, which is going to be a half, and then a third, and then a fifth, then a seventh, and then an 11, 13, 17, and so on and so forth, okay? Now, the problem with this is that there's no real useful way to get a list of the primes. Well, Euler figured something out. He was able to get all the primes in a kind of an equation. And what Euler showed, and I'll be doing this for us because it's a really good application of what we're going to be learning towards the end of the chapter, that this sum diverged. Okay. So what that meant to him was that the primes aren't really scarce. They're kind of abundant, because if they were scarce, like these perfect squares on the number line, the further out you get, I mean, it's hard to find them, okay, that there's fewer, I guess, in terms of infinity type numbers, fewer of these perfect squares than they are of the primes. Okay. So anyways, we'll talk about that a little later. All right, so an example that we could do here would be something like this. N equals 0 to infinity, 1 over n squared plus 1. Okay, so we can do the integral test. We'll go from 0 to infinity, 1 over x squared plus 1 dx. And this stuff has just got to roll off your tongue at this point. That's the tan inverse of x evaluated at infinity and at 0. And so this is going to be the limit as, let's say, t goes to infinity of the tan inverse of t minus the tan inverse of 0, which is just 0. Okay, so what is the limit as t goes to infinity of the tan inverse of t? So if you guys remember what tangent looks like, it has an asymptote here and here, and this is at pi over 2, and the graph goes like this. So the tan inverse graph is going to have asymptotes like this, and it's going to go like that. So as t goes to infinity, tan inverse of t is trying to go to pi over 2, which converged. So due to the integral test, this sum, 0 to infinity, 1 over n squared plus 1, converges. Now they're in Compton. All right. Now, this was a great application of integrating. I would certainly want you to do this because it's another integral for you to do. Okay, but we already know that the sum from 1 to infinity of 1 over n squared converges. This thing is not the same, but I mean, when n gets really, really big, does this one really matter right there? Remember, we're going to infinity. So that means, you know, n could be 10 trillion, billion, billion, trillion. And then you just add 1 to it. Okay. Well, we should be able to maybe say something a little bit better about this. So we are in section now, moving into section 11.4. And these are called the comparison tests. Okay. So let's look at something here, all right? So suppose I've got two sequences, AN and BN, where everything is still going to be positive. And I have the two series, the sum of the ANs and the sum of the BNs. Okay, now it's assumed that this sum is going off to infinity. It's an infinite sum. Okay, the starting point, like I said, and is not really relevant, only to like if you were trying to find what it adds up to. But most of the time, we're not going to be concerned with that. Okay, so number one, what if this is the case for all n, and the sum of the BNs converges? Then wouldn't it stand to reason that the ANs must converge? Okay. Now we'll prove this stuff, you know, but it just kind of stands to reason, I think. Like if you're adding up all these B's and they're adding up to some finite number, and each one of these ANs is smaller than its corresponding BN, then this sum must converge. Okay. Number two, again, if this is the case for all n, and if the sum of the ANs diverges, then that would force the sum of the BNs must diverge. Okay. So the ANs are adding up to infinity. Remember, everything's positive here. Okay. So diverging means you're going to add up to infinity. Okay. You only get weird kind of things when we start doing alternating and negative stuff, and that's the next section. Okay, so now let's see if we can follow this here. Okay, you don't got to write it down, it's on the book, I guess, but just try to follow it. So we're going to let Sn be the sum from k equaling wherever we started to n of the AKs, and we're going to call, let's call Tn the sum k equaling 1 up to n of the BKs. Okay. And okay, now case number one, let's suppose that this thing converges. So that implies that the limit as n tends to infinity of t sub n which is the sum, k equaling 1 to infinity, of b sub k is equal to some fixed number t. Oh man, they switched it to the World News Tonight. I don't care about that. I want to go back to car chase. Car chase. Channel 9, car chase.
Find it.
Maybe the Family Feud. Yeah. No, damn it. Come on, what's more important than a car chase? It sucks. I have to find it. Streaming. Okay, so now because since AN is less than BN, 0, which is bigger than this guy, less than TN. Okay? And so the limit as n goes to infinity of the Sn, this is going to be less than or equal to the limit as n goes to infinity of the Tn's, which we found to be t, which is finite. Okay? All right. So now basically for this discussion here, I'm talking to Eduardo and anybody else that's thinking about taking more math than just these calculus courses. Okay, so all we have established here is that this limit is sitting somewhere between 0 and t if it exists. And I'm sure Takasaki, I don't even know if he's still alive, but I bet you he could come up with something that's really bizarre. So what we have to do is we have to get a little bit more tricky with it. Okay, so let's look at the sequence Sn. The sequence Sn, okay, Eduardo, make sure you get this all down carefully. This sequence is an increasing sequence because Sn plus 1 is equal to An plus 1 plus Sn. Okay, and since we're assuming that everything is positive, back up here like that, we see that Sn is increasing. Also, the sequence Sn is bounded above by this number t. So according to the result that we proved, having to use the completeness axiom, the limit as n tends to infinity of the Sn exists. Call it S. So that would tell us that the series of the ANs adds up to S. And so this thing converges. Okay, so we did have to do a little bit of maneuvering there. All right. All right, what about the second case? All right, so I want you guys to try this, okay? For those of you that are interested. If the second case is we were going to say, all right, let's suppose the ANs diverge. So we're still going to have this line, right? Okay. Now, when you use the limit goes to infinity of Sn. Because everything's positive, Sn is going to infinity. So that Tn has no choice but to go to infinity, therefore it diverges. So that's me talking through it. What I would want you to do would like try to write it out, you know, and then maybe we can find a way that I can look at it or something just to see if you're doing it right. Okay, so for number 2, you do it. Okay. Okay, so now we go back to this problem that we had to haul out the integral test for 1 to infinity of 1 over n squared plus 1. So let's recognize something here. 1 over n squared plus 1 is less than 1 over n squared, right? When you make the denominator bigger, the fraction gets smaller. Okay? And the sum of the 1 over n squared converges. So by the comparison test, our series also converges. Okay? And for that matter, you could probably do this with any quadratic, you know, like n squared minus 3n plus 2, or plus 3n plus 2. Well, that's going to be smaller than this sum, because when I take something out of the denominator, it makes the fraction bigger. And again, this thing converges. So this guy converges. All right. All right. How about we do this? N equaling 2 to infinity of the natural log of n divided by n. Okay, so do you think this is going to converge or diverge? Well, we know the 1 over, we know this diverges. We know that much. That's the harmonic series, right? So what's going on? What's going on with the numerator? Well, I'm starting the sum at 2. So what's the natural log of 2? Some fraction, okay? But what's the natural log of 3? Let's do it on your calculator real quick. Get your thing out here. Wait a minute. What is this?
$1.09.
Yeah.
Yeah.
1.09. Wait, something's locked up on my thing. Give me a second. I got to figure this out. Okay. So the natural log of 3 gets bigger than 1. And if n is bigger than or equal to 3, the natural log of n is going to be bigger than 1. So if I was to look at the sum starting at 3 and going to infinity of the natural log of n over n, this would be larger than the sum n equaling 3 to infinity of 1 over n. Okay? And since this guy diverges, and this guy is in front of a diverging series, we must have that the sum n equaling 3 to infinity, the natural log of n over n, diverges. Hence, the original guy also diverges, because remember, adding or removing a finite number of guys from the sum isn't going to affect the outcome. It'll affect what it adds up to maybe, but it's not going to affect convergence or divergence. Okay? So if you want to get something that is bounded, if you think something is diverging, you want to compare it and get it in front of something you know that diverges. And if you think something is converging, you're going to try to get it behind something that converges. Okay? So if let's, for example, try this thing. N equaling 0 to infinity, 1 over n factorial. Okay? Where we all know that n factorial is n minus 1 minus 2, 2 times 1. Okay? All right, now these numbers are getting huge fast. So I think this thing is going to converge. Okay, so the problem here we need to find the sequence, find a sequence Bn such that 1 over n factorial is less than or equal to Bn for n eventually bigger than some number. We don't have to have it right out the gate. We just have to have it eventually bigger. And the sum of the Bn's converge. Okay, now this is going to be really difficult with this guy. So we might have to wait for a much easier test or a more penetrating test. Okay, so what do you think? If I look at like 1 over 5 factorial, 5, 4, 3, 2, 1, I guess we could say that that's less than 1 over 5, right? And for that matter, 1 over 6, the next one, 1 over 7. Okay, but that's not going to help us because we think this converges and we're going to get it behind a diverging series. Okay, so that's not much help. Okay, so nor is it for this one. We don't really have to get too carried away here. The sum k equaling 2 to infinity, about 20 to infinity, 1 over k squared minus 1. Okay, now again, by the same principles and just thought process, when k gets really enormous, this minus 1 isn't really going to affect very much. Now, we could do partial fraction decomposition on this thing and then do the integral test on it. Okay, but it seems kind of unnecessary, at least to me, because we know this thing is going to converge. Okay, problem is that 1 over k squared is smaller than 1 over k squared minus 1. The sum of the 1 over k squared would then be less than the sum of 1 over the k squared minus 1. This thing converges, but we would have needed it over here in order to draw our conclusion. Okay, so looks like we're going to need a new test, all right, because this has got to be the case, all right? So we'll develop a new test, which is called the limit comparison test. Okay, so let's suppose we have these sequences AN and BN, AN positive, BN positive. We're not going to assume any one of these guys is bigger than the other one, okay? And we have the corresponding series. Some of the ANs, some of the BNs. Okay, so there are 3 conclusions that we're going to draw here. The first one is the main one, okay? So if we were to consider the limit as n tends to infinity of AN over BN, if this number is C, and all it needs to be is some positive number, remember, everything's positive here, okay, so we don't have to worry about any negative, then the series sum of the ANs and sum of the BNs both converge, or they both diverge, meaning they do the same thing. Okay? All right, now we're going to pay for this result, and payment comes in the form of a proof. Okay? The other 2 are these guys. If the limit as n tends to infinity of AN over BN is equal to 0, well, if that was equal to 0, wouldn't that tell you that the BNs are bigger than the ANs if it's going to 0 eventually? So if the BNs converge, then the sum of the ANs converge. Okay? Number 3, if the limit as n tends to infinity of AN over BN is positive infinity, that would mean that the ANs are going bigger than the BNs. And so, and if the sum of the BNs diverge, since the ANs must be bigger than those guys, then the sum of the ANs diverges. Okay? I give you a second to catch up there. All right. So let's prove this first one. All right. Now, I always say the same thing in here, and you've heard me say it already, that I'm not going to ask you to prove stuff. I know who my customers are, okay? But I find over the years that it's really helpful to people if they can just follow it. Try to follow along as you can. Don't be so busy writing stuff down. Just see if you logically can follow this. Okay, so let's suppose that the limit as n tends to infinity of an over bn is equal to c, and c is a number bigger than 0. Okay, now one of you might be getting ready to ask here, well, what if I called my an's bn and you called, and we had them reversed? Well, if the limit as n tends to infinity of an over bn is equal to cn, is equal to c, then what would this limit be? Anyone?
C.
An over bn goes to c. So what does bn over an do?
C.
No, almost.
0.
Negative
1
C.
over c,
Oh.
which is still a positive number anyway, right? Okay, so we don't have to worry about, who called what. That's all we need, okay? Okay, so this means for any epsilon bigger than 0, there exists a capital number n bigger than 0, such that if n is bigger than this n, the difference between an over bn minus c can be less than epsilon. Okay, so that's the definition of the limit. Got it? Okay, so we're going to get very specific here. So I'm going to let the epsilon equal c over 2. Okay? So that means there exists an n greater than 0 such that n bigger than n would imply that an over bn minus the c is less than this c over 2 guy. Okay? So now I'm going to go back to intermediate algebra and I'll undo the inequality. Undo the absolute value. Negative c over 2 less than an over bn minus c less than c over 2. And this is all valid when n is larger than n. Okay? So now I'll add c everywhere. So I'm going to get c over 2 less than the an over the bn less than 3c over 2. And this is when n is larger than n. Okay, now remember the bn was positive. So I can multiply everything by it and not mess it all up. Okay, so this means that I'm going to have c over 2 times the bn less than the an less than the 3c over 2 times the bn. Okay. So now I think we're ready to strike here. Look, if the sum of the bn's converges, then the sum of 3c over 2 bn converges. So by the comparison test, not the limit comparison test that we're proving, but just the comparison test, the sum of the ANs converges. Okay? And if the sum of the BNs diverges, so would multiplying everything by this positive number. As we've seen, it doesn't really affect anything. This guy diverges, and so that would be pushing the ANs to diverge. Okay. Now, as far as numbers 2 and 3 go, you try to work that out, especially Eduardo, who's a math major. Okay, because you're going to be asked to do this stuff, and you might as well get used to it now. It's going to be a similar argument with mine. Okay, to do number 2, well, if this is 0, if this limit is 0, okay, then that means I can get AN over BN as small as I want, say in magnitude less than epsilon. And then you just run the playbook again, only this time you don't have to worry about 2 different directions. Okay. Okay, so let's look at this guy again. So now where I'm looking at is the sum of the 1 over n squared minus 1. So we'll call that AN. BN, 1 over n squared. The limit as n tends to infinity of AN over BN, limit as n tends to infinity, okay, so that's going to be n squared minus 1, and then the n squared goes up here. Okay, here we are, night 2 this week. What's this limit?
Pi squared over 6?
N squared over n squared minus 1.
Sine inverse?
No. What's the limit? If I asked you what's the limit as x tends to infinity of 3x squared minus 4x divided by 2x squared.
Oh, that would be 3
by,
halves. So this is 1.
Right, 1. Okay. So this stuff kind of comes at you fast. Under a normal semester, it's fast. And in the summer, it's twice as fast. Okay, so you're just going to have to figure out a way to separate ideas in your head. Okay. All we needed that to be was positive. And so, because the BNs converged, this is going to tell us that the sum of the ANs converge. All right. So that's that limit comparison test in action. Okay. All right. So for a guy like this, and I'll start the sum at n equaling some big ass number m and going off to infinity, 3n cubed minus 2n squared divided by the cube root of n to the 10th minus 4n squared. Converge or diverge? Okay, well, yeah, I just breathe some in. Okay, so one of the down things about the comparison test is the go-to thing. If anything else fails, you always go to the comparison test. There's going to be some that, you know, we're going to have to really work hard with. But if you want to use these tests, you kind of have to have an idea ahead of time. Okay. So I'm going to compare this to B sub n, which is going to be n cubed divided by the cube root. Do that again. Divided by the cube root of n to the 10th. These are the dominating terms, okay? And so that's going to be n cubed divided by n to the 10 over 3, right? And so that's going to be n to the 9 over 3 over n to the 10 over 3. So that's going to be 1 over n to the 1/3. Okay. So I'm taking the dominant terms, and this is what I'm going to compare it to. Okay. Now, we know what this does. Converge or diverge? The exponent is 1/3.
Isn't that
One-
converge?
Converge. 1 second.
Ah,
You guys are batting a perfect 0. Remember,
hooray!
the P here is 1/3. That's less than 1, right?
Yeah.
See how all this shit just piles up on you? This is what happens in the normal semester. The class is 2.5 hours long. Sometimes we go for an hour and a half, and that's the end of the day, because it's just too much coming at you, you know? So that's why I try to blast through the stuff early and then get to spend as much time with this. Trust me, it's going to be hard. All right. Before you guys start looking, you know, when I post the test tomorrow or Thursday, before you guys start digging into books and trying to figure out, you know, ways to cheat your way through this or copy. And again, I don't care. I know you can do whatever you want, but at least try to do these. And then when you look up the answer, you'll appreciate it. You'll a lot more. Okay, so our AN is this 3n cubed minus 2n squared divided by the cube root of n to the 10th minus 4n squared. And the BN is going to be 1 over n to the 1/3. A sub n over B sub n is going to be the n to the 1/3 times the 3n squared minus 2n squared, 3n cubed minus 2n squared, all over this cube root of n to the 10th minus 4n squared. All right. So if I kind of expand this out, it kind of looks like I'm going to have n to the 3 plus 1/3. That looks like n to the 10/3 minus 2, n to the 2 is 6 over 3, 7 over 3, divided by this cube root thing of n to the 10th minus 4n squared. Okay, now if we take the limit as n tends to infinity, we're going to get infinity over infinity. All right, so maybe we can do something here. if we multiplied the top and bottom by 1 over n to the 10 thirds power. And oh, I forgot there's a 3 there. Okay.
With
Oh,
answers.
n to the 10 over 3. Okay, so you pick the biggest exponent you see, and that's looks like it's going to be that. Okay, now because of my experience, I know this limit is going to exist. It's going to be a number. Okay, but that's just because it's me, right? Okay, so now if I distribute at the top, I'm going to get a 3 minus 2 times 1 over n to the first power divided by, okay, now I'm going to take 1 over n to the 10 and write this as 1/3. And then this I'll write as n to the 10th minus 4n squared to the 1/3. Okay, now the way that the exponent rules work, down here, it's going to be 1 over n to the 10th times n to the 10th minus 4n squared to the 1/3 power. 3 minus 2 over n divided by 1 minus 4 over n to the 8th power to the 1/3. The limit as n tends to infinity of this an over bn thing, the top goes to 3, the bottom goes to 1. 3 is finite. I mean, it's positive. So since the comparing guy, the sum of the bn's diverged, that's going to imply that our series also diverges. Okay. Okay, so he's got, a few of these guys in here like this in the exercises. And there's a few problems from the exercises I want to do just because they're kind of this flavor. Shut this real quick. All right. So any questions on this problem that I just did? Or is it just so much that you don't even know what to ask?
It's pretty, it's not super clear, but like as long as we can, I'm gonna try and do a few problems on the homework for this.
All right.
'Cause it's pretty extensive.
Yeah, and these conclusions are going to start getting odd, like if the limit is bigger than 1 versus less than 1, or something along those lines.
But what I've seen so far from what your examples you're showing us right now is that if like the bottom is bigger and the top is the top is smaller than the bottom, there's a possibility it's going to converge.
Okay, so now that you've seen this, this was the key thing, to pick out the dominating exponents.
Exactly.
Okay, and then simplify it, and that's what you're going to compare to. Okay, these next problems are just pretty much in the abstract. Okay, so this used to be called number 44 in the book. I don't know if it's even in the book anymore, the current book. If an is positive and the sum of the ANs converges, what about the sum of the natural log of 1 plus a sub n? Converge or diverge? Okay, now before we all start guessing here, let's talk about this. Okay, first of all, the logarithm takes numbers and makes them even smaller. So even if, because this thing converges, that's going to imply that the ANs go to 0. Okay, that's that criterion for convergence. All right. So because we're in the comparison test right now, okay, I can't take the log of 0. So this is why I have to put the 1 right there, or he had to put the 1 right there. Okay. Now, because log takes numbers and make them smaller, what I'm going to do is I'm going to see if I can bound this thing. Okay. So let's let f of x be this function. The natural log of 1 plus x minus x. Okay, I'm going to try to show that the natural log, of 1 plus a sub n is less than a sub n for n eventually big enough. It might not happen right off the bat, but if it eventually starts converging, and there was this professor at Cal Poly, he was really old when I was there, Herzog. I still have some of his books. He had examples of these crazy series that, I mean, you couldn't bound it until you're past like n equals 1,000,000 or something like that. Okay, so this would be equivalent to showing the natural log of 1 plus a sub n minus a sub n is negative. Okay, so that's why I created this function. Okay, so let's see here. What's going on with this function? Well, first of all, what's f of 0? It's going to be 0, right? The natural log of 1 plus 0 is natural log of 0. And then minus the 0 thing. All right. Now, if we're going to try to show that this thing is negative, it's already starting at 0. So what do you say we look at f prime of x? Why would you look at f prime of x? Well, if the function is increasing or decreasing, we can get that information out of the f prime of x, right? Remember, if f prime is positive, you're increasing, and if f prime is negative, you're decreasing. Okay. Trying to find my car chase. And shit. I'll leave it on channel 9. Then when the news comes back on, maybe they're still racing around. Okay, so let's do f prime of x. So that's going to be 1 over 1 plus x minus 1. Actually, you know what? Let's, because it's easier to look at it this way, let's switch it. So let's let f of x be the guy x minus the log of 1 plus x. So we're trying to show here that a sub n minus the natural log of 1 plus a sub n is positive. Okay? Doesn't change f of 0. It's still 0. F prime of x, this is 1 minus 1 over x plus 1. Okay? If I common denominator this, it's going to be x plus 1 minus 1 over x plus 1, which is equal to x over x plus 1. So f prime of x, which is equal to x over x plus 1, is going to be positive. Well, let's see where it's going to be positive. First of all, if we plug in a number over here, it's going to be positive, right? You plug in a negative number over here, it's going to be negative, negative a half, right? And then if you plug in a negative over here, it's going to be negative. Okay, now the only thing we care about is this, right? Because remember, the ends are integers, or positive integers. Okay, so f of x is increasing on the interval 0, 1. Whoops, 0, infinity. Okay. So since f of 0 was equal to 0 and the function is increasing, we can conclude that f of x is positive on the interval 0 to infinity, i.e., if x is bigger than 0, comma, x minus the natural log of 1 plus x is positive, i.e., x is bigger than the natural log of 1 plus x. So that means that the natural log of 1 plus a sub n is going to be less than a sub n. Remember, all x had to be was positive, and each one of these ANs is a positive number. Okay? And so, since this sum of the ANs converges, we conclude that this sum must also converge. Okay? All right. Here's another one I got out of the book. Suppose that our ANs converge. AN is positive. What about the sum of the sine of AN? Converge. or diverge. Okay. So I want you guys to play around with this thing for 5 minutes and see what you think, okay? Because if I just do it, you're just gonna, it's another me copying it down. But I want you to at least try something, and maybe when I chime back in, I can nudge you the right way.
So we're like supposed to be doing this problem, and he walked away. Is that what's going on?
Yeah, but even if we mess up on it,
Eduardo, if you mess up on it, you're gonna get a 0 in the class. Okay, I just made that new rule, so you better not mess up. Because
what?
if only if you, but if you mess up at all, it's a straight 0 for you, man. So I don't even want jokes of jokingly messing up, because that's 0 out of 100, the whole class.
Oh, really?
It will be between -1 and 1.
Okay, that's what I was just about to ask. Who is recognizing here that sine is no bigger than 1, no less
Yeah.
than -1? Okay,
Yeah.
that part of it was good.
Yeah.
Okay, so that was one thing I definitely wanted. Now, this next piece might not flow so nicely, okay? So the sine, as you know, once we get past pi, then the sine becomes negative, right? For a
Right.
little while. And, we're only dealing with positive series here, okay? The next section is when we start to alternate them. So what we're going to do is make the observation, since this guy converges, the limit as n tends to infinity of the ANs is equal to 0. So there exists an n, not in lowercase n, a big N. There exists a capital N bigger than 0, such that if n is larger than this n, the a sub n is going to be between 0 and pi over 2. Okay, so I wanted to do that, so now I don't have to deal with any negatives. Okay, all right, so for an sitting in the interval 0 to pi over 2, the sine of x, or sine of an, is going to be positive, and it's going to be less than or equal to 1. So that means that the sum, when n starts at n plus 1 and goes to infinity, of the, that thing's positive, the sine of the an, and that's going to be less than the sum starting at n plus 1 and going off to infinity of just the ANs, which converges. Okay, so by the comparison test, straight comparison test, this sum, why does it do that? This sum n equals n plus 1 to infinity, the sine of an converges. So if you add back all of the rest of them, finite number, however many we wanted to start with, but the whole series is going to converge. Okay, now one of the things that you guys are going to have issues with is looking at the limit of the sequence and then comparing that kind of to the limit of the series, and it's hard to separate ideas with this for some people. If you've had this once before, maybe this is going down a little easier the second time. Honestly, guys, I really didn't get good at this stuff until I started having to use it in my physics courses. When we started having to do this stuff in physics, and physics is really what I was interested in. I'm not supposed to be doing this. I was the guy that was supposed to discover the Higgs boson. But anyway, I ended up here in sitcom Community. Pretty funny last night. It's like all of the stereotypes of you guys. Like, I think we made it through. We're almost at the end of season 1, I think. We're 6 episodes in.
Oh,
Yeah.
you know where I think there's at least 12, man, for season 1.
Oh, okay. Well, they go quick, they're only 20 minutes long.
Yeah.
So here's another one. Interesting guy. It used to be called 46. I don't know what it's called now. So let's say that we're given that AN and BN are both positive, and both the sum of the ANs and the sum of the BNs converge. What about the sum of the product of these two guys? You can hear the musical stylings of Guns N' Roses in the background because my oldest son, 20-year-old, favorite band in the world is Guns N' Roses. It's 20.
Let me guess, Chinese Democracy. That's his favorite album. The best one.
Now, he doesn't really know any songs off of Democracy. I was taking him. I had, the GNR show is supposed to be in 3 weeks.
I'm sure it will be.
Well, yeah, it's over now, but I was taking him. I had floor seats I had floor seats on the Duff side, stage left, I guess. Should you call that stage left? When you're looking at the stage, the left is stage left, right?
It's from the stage looking out at the crowd, so that'd be stage right, I think.
Okay.
You're looking at them and they're on the left. I believe that's stage right. Is it Forum or where were you guys going?
The SoFi.
SoFi? I don't know SoFi.
The Rams and Chargers new football.
Oh, did that ever get built?
Oh yeah, it's getting built. Construction is still going. Just like at the division meeting on Friday when they're talking about don't go to campus and this, that, and the other, and I'm saying, guys, I go to campus. It's busy over there. There's construction workers and foremen and this, that, and the other thing. So, anyways, they're still building that.
I just got an email about the housing at the school today.
Our anniversary, my wife and I, our anniversary is in, what's the date today? 21st?
21st.
Yeah.
Yeah, so it's in like 11 days. And we were going to go to Kenny Chesney at the same place, SoFi Stadium. And that's not happening.
Good luck figuring out something to do. We didn't do anything on our anniversary because of the same thing.
No, we're all into kayaking now.
Oh, good. Okay, you can do that.
Yeah, so. And then anyways, let's finish this problem. All right, so let's see here. What do you think? Remember that since since the series AN is finite, the ANs go to 0. Same thing for the BNs. The sum of the BNs is finite. That would imply that the BNs go to 0. Okay. Now this one is really kind of easy. Okay. Since AN goes to 0, there exists a number M such that if N is bigger than this number N, AN, which is positive, remember, will be less than 1. So if I look at this sum starting at M plus 1 and going to infinity of AN times BN, well, that's going to be smaller than the sum going from M plus 1 to infinity of just the BNs, which we know to converge. So the same conclusion. By the comparison test, and don't underestimate the comparison test. We needed that bounded monotone sequence to have a limit in that proof. The straight comparison test is the crudest test, but it's also the go-to when nothing else works. You know? Okay, well, anyways, so that means that these two guys, the product converges. So that means doesn't matter where you start it, where you end it, that thing is also going to converge. All right. So dig around in the problems here. Let me see if I find anything new. Blah, blah, blah. Blah, blah. There we go. This is an interesting one. The sum n equals 1 to infinity of, I either need to stop smoking so much pot or get better, higher power reading glasses. 1 over n to the 1 plus 1 over n. Converge or diverge?
My money's on Diverge.
Money's on diverge?
Yeah.
Yep, and I think you're the winner chicken dinner. Okay,
I
so
win.
here's what we know. Here's what we know. We know that if we had a fixed number epsilon, if epsilon is bigger than 0, this sum starting at 1 and going to infinity of 1 over n 1 plus epsilon converges. I wrote that down yesterday. And I said, okay, and I even did one. Epsilon is 0, 0, 0, 0, 0, all the way across 1. Convert. Mm-hmm. Okay, well, the thing is here is epsilon is a fixed positive number. This 1 over n right here, that's going to go to 0. So I'm thinking this thing is going to diverge. Okay. So let's haul out the limit comparison test. AN is going to be our thing. Okay, now what is the series that's the prototype diverging series that had a chance to converge? The harmonic series, right? Okay. So if I look at AN over BN, then that's going to be N divided by N to the 1 plus 1 over N. That's N divided by N times N to the 1 over N. That's 1 over the nth root of n. So what is the limit as n tends to infinity of an over bn? It's the limit as n tends to infinity of 1 over the nth root of n. Now, I started yesterday's class with, okay, these are some important things you probably want to remember. And one of them was this limit. Do you remember what this limit is? The nth root of n? 1.
Oh.
So the limit as n tends to infinity of the nth root of n is 1. The other result we're going to need eventually is, I'll keep writing it down. Okay, well, all we needed was that to be a positive number. Okay, so the series AN and BN both diverge because the BN diverged. Okay, so that was a problem in there. Okay, maybe we now have enough n equaling 1 to infinity 1 over n factorial. All right. So what do you think? We think this is going to converge. We've already had this discussion. Now that we have the limit comparison test and the comparison test, maybe we can say some stuff. Okay, so let's see. We know this is going to converge. So if AN is this 1 over n factorial, maybe we can do a limit comparison test with this. Okay, now I don't think this is going to go anywhere. AN over BN is equal to n squared over n factorial, which is n divided by n minus 1 factorial. And I don't know, man. I don't know if that's getting us anywhere. Maybe he wants
that. Doesn't it just get closer to 0, but it doesn't go to 1?
Yeah, I mean, there's going to be a real quick way of figuring this out. Okay, but this one, like, if I had n, n minus 1, n minus 2, 2 times 1. Okay. Now so this is for this particular n, okay? So is this less than 1 over n squared? See, what I can say is this. I can say that 1 over this n factorial to 1 smaller than, remember, all these things are positive integers, okay? So that's going to be smaller than n minus 1, which is equal to 1 over n squared minus n. Okay. So is that true? Let's do an experiment. 1 over 6 times 5 times 4 times 3 times 2 times 1. Is that smaller than 1 over 6 times 5? Yeah, right. Okay. So from the limit comparison test, the sum n equaling 1 to infinity of 1 over n squared minus n converges. Okay, we would call an this 1 over n squared minus n, and the bn is going to be 1 over n squared. An over bn is going to be n squared over n squared minus n. Okay, here's your guys' 17th chance. What happens as n tends to infinity of this?
1.
There you go. We finally got it. Okay, so what we can say is that because this thing converges and this thing looks like, I didn't have anything there, and 1 over n factorial is smaller than 1 over n squared minus n, for n maybe sufficiently large, like maybe you can't obviously use 1, right, in division by 0. So you'd have to use maybe starting at 2 or something like that. Okay, but in any event, so this implies that the sum k equals n plus 1 to infinity of 1 over k factorial converges. That's going to imply that the sum, doesn't matter where you start it, 1 over k factorial converges. All right. Okay, well, in section 11.4, do a bunch. Okay, now I'm kind of figuring things out here. Like, how do I think this is going and whatever, and how can I make it better? Stuff like that, you know? So I think it's going to be kind of important for you guys to like at least be on top of the problems from today tomorrow. Like, you can't put it off. Like, you know, you have to go through and get this limit comparison idea down. You know, it almost like be worth it for you guys to like kind of all organize in your own Zoom meeting, and then, you know, go through problems. Because again, like, just watching me do them and coming up with all the $1 million ideas, it's not really going to help very much. Number 27 is the one that you might want to think about. 28's interesting. Okay. So I don't want to just keep doing them. I want you guys to do them. I mean, and if you run out, just do some more from somewhere else. Okay.
Okay.
So I'm still waiting for my car chase to come back on. Now this is where I would normally go right into 11.5 and just introduce it and then say, okay, see you tomorrow night. It's whether we're having class like this or in person does not change the pace at which I need to do this stuff. You know, for those of you that have already had this before, yeah, you're going to sail right through it. I'm finding that as I talk to the students, a lot of the foreign students, they've had exposure to this stuff. You know, like it's taught in the, I mean, we kind of introduced this series stuff in Math 30, but they get full blown into this. I mean, I think I told you guys, I saw the entrance exam to get into university and for mainland China years ago to go major in business. And then one of the questions, state and prove the mean value theorem, so if you're a foreign student, maybe, you've had more exposure to this stuff. I can tell you that in our own dumb American high schools, not gonna, we don't, we leave no child behind is what we do. And we have an adjunct, Frank Miola, this old guy from Staten Island,
Staten Island.
he's like, I can't, he's a high school teacher, he's a retired high school teacher. I'm telling you, some kids need to be left behind. He says.
It is it's an interesting thing, the no child left behind policy, like especially if you're somebody who learns very quickly. I feel like it'd be really discouraging if you're trying to learn and they're like keeping you on something that is really, really simple, because it's difficult for a lot of people. But I don't know. I didn't really deal with it, so I don't know too much about it. Just the concept.
This kind of thing happens time to time in high schools. My high school that I graduated from, when I was starting college, my youngest brother was there. And what they did is they decided to detrack the high schools, meaning,
Okay.
you could take a college, prepping you to go to college, like you're going to take some history course versus the non-college track. I think they call it A and B or something like that.
Okay.
And the thinking was, well, when we take all of the advanced people out of the room with the slower people, then they don't have a chance to help the slower people. So we need to keep them with the slower people so the slower people can catch up. How is that fair to that girl that's fast? I mean, she didn't sign up to help, If she did,
she's a helper.
No. And so this happened at my high school. They detracked everything. I mean, it's stupid.
I feel like if we were to structure our schools differently, then we wouldn't have this problem. Japan does that, where if you're slow, if your test scores aren't even on the board, you get sent to a different school that, where all the slower kids that are just like
Trade
you,
school.
get put into that school, so that the averages are the same there for that school, right?
Yeah. It's like that in
you have the smart kids at the other school,
It's like that in Eastern Europe too.
Yeah, it's not a problem, because eventually, that kid will eventually get into a job just as easily as a guy that would go and get another job, but he would still qualify for that job based on where he got to, and leave all the good, all the really big jobs to people that did qualify, that did get the grades, that did, are at that level.
I think the only problem, because I think that way is good too, but the problem with a lot of these countries where they do have that, or I don't know about Europe, but at least Japan has the highest suicide rate, because if you don't do well and you don't have a good job, there's kind of no hope for you. One of the reasons why you see so many children coming over, or not children, college students coming over from China, is because unless you can get into the top 4 universities in China, the rest aren't considered very good. So, they're not bad, but they're just not nearly as good. So if you're not on track to get in the top 4, and the only way to get in is they have this exit test you take to get out of high school.
Uh-huh.
You have to do really good at that. So if you don't test off the charts for that, it's and your parents have some money, it's send them to US school. It's way easier. And then they'll learn English and blah, blah. And so I see, I don't know. I see the value in both of the ideas, but the no child left behind policy at a young age to me is just now looking back at it, I was homeschooled through 11th grade, and then I went to private school. I'm happy my parents did that, because I was doing algebra 2 at 8th grade, because I liked math when I was younger, you know what I mean? And I don't know if you can do that at 8th grade. I don't know what the options are, and if you're like me and you liked hanging out with friends, when I went to private school, I never did AP classes because all my buddies weren't in AP. So I didn't want to be in AP classes. So like, it's I think it's a tricky thing all in all, like, you know,
In
but
middle school, I remember that I qualified because of my grades in school a little bit higher than everybody else in my classrooms for all of the subjects. They entered me into a writing contest that let me go as a foreign exchange program for like the summer school
okay.
in Japan. Did it, got there, and was just blown away with the whole testing thing that they did there. I'm like, damn, they're gonna send me. They're gonna figure out I'm completely an idiot. For a week, you know?
Well, they
But,
also, oh, go ahead.
I made it through the summer, but I was just blown away how when you sit down and you take those exams, that they're actual exams, like they're no joke kind of exams.
Yeah, it's not like our standardized testing, which I remember thinking was such a joke. I was so pissed off that when I went to school that our school did it, that I purposely answered everything wrong that I could just to lower the testing grade at the whole school. I was like, it was just a waste of time. It was garbage. The whole thing is trash. The school I went to closed down anyway, so it doesn't really matter. But yeah, I think that stuff, those standardized testing, the SATs, all that stuff. Like I took the SATs and I took the SAT 2s or SAT 9s, I think they're called or whatever. Like yeah, where you take subjects. Because I'm such a dumb idiot when it comes to signing up for stuff that I thought that was the SAT. So I took the SAT 9s and I realized, oh, this isn't the right thing. So I took the SATs and I don't know. And then it's like, well, I could get into good schools and pay a ton of money to do my GEs, my general education. But it's like my parents were like, don't do that. Go to OCC. So it didn't even really matter. Like it was like, yeah, man, I think our whole education system's going to be a very it's ready for an upheaval, but
it's pretty backwards. It's just
yeah. I mean, what are you gonna do though, right? Like
we're concerned about suicide rates when we should be concerned about production and monetarization of jobs. So that way when you're underneath the cutting board,
yeah,
you're getting worked on by somebody that qualifies.
Oh yeah, man. But the problem is you literally can see that right now. Like nobody cares about jobs this year. Like that is like you're a monster if you do. So we can't talk about jobs and we can't talk about any of those things. And surprisingly enough, actually, the suicide rate from what I've read is the highest it's ever been this year historically, but nobody's been talking about that. But it's like monumental like this year. But like I said, it's not part of the news cycle. So
that
yeah,
doctor that contracted COVID and then killed himself.
Yeah.
Mm-hmm.
They chalk that up to COVID.
Oh yeah,
and not suicide.
Yeah, that's a very common thing. Yeah, man, the whole thing's crazy. But yeah, I do agree that like in some ways, when it comes to jobs and the economy and the good